Okay, let's take a look at the set of prime numbers. So the primes are really interesting. They just seem to pop up at random as you go down the integers. So I've written down the first few here: 2, 3, 5, 7, 11, 13, 17, 19, 23. Let's see, did I forget any there? 29, 31, 37, 41, 43, 47. 51 is a multiple of 3, so 53, 59, 61. So I think I've got all of the first few primes. So the question is there any pattern to them? Can we predict when the next prime will arise? And I've just marked down a few questions you can ask. And how many primes are there? Is it a finite number? Is it infinitely many? How many primes are there up to a given value, n? So what's the density of the primes, in other words? What's the size of the nth prime? Can we make a prediction on that? How about the gaps between consecutive primes? Sometimes there's small jumps, like 2 apart, and sometimes there's bigger jumps. There's 6 apart. Can we say anything about the size of those gaps? And so you can go on asking a variety of questions. Okay, let's prove first that there are infinitely many primes. This is a theorem that goes back to Euclid and will in fact give the type of proof that Euclid gave. So it's simply a proof by contradiction, and you've probably seen this before. So we suppose that there exist finitely many primes say P1, P2 through Pk, and we want to derive a contradiction. So what do? You consider some integer such as the product of these numbers plus 1. So I'm trying to create some number that could not possibly be factored using just this set of k primes. So I'll take the product of those primes and I'll just add 1 to it. Well, this is a positive integer, and so by unique factorization theorem, the fundamental theorem of arithmetic, it must have some prime factor. So n has a prime factor. And these are the only set of primes that exist, P1 through Pk, so it must be one of those primes for some I. Well then, this prime Pi is a divisor of n, and it's a divisor of the product of all of the primes, because it's sitting as the ith prime in that product. So it's a divisor of 2 consecutive numbers, that is, thus Pi divides n minus this. But that difference is just equal to 1. A contradiction. Okay, so it's very easy to prove there exist infinitely many primes. So let's prove a slightly stronger theorem. Take a look at the harmonic sum of the primes. So in this theorem, I'll use log to denote natural logarithm. That's a convention in number theory. It's the only logarithm mathematicians generally work with, is the natural logarithm. So we claim that for any natural number n, the sum of the reciprocals of the primes up to n, so p is less than or equal to n, is bigger than the natural log of n plus 1 minus 1. So if I look at the infinite series of all reciprocal primes, 1/2 plus 1/3 plus 1/5 plus 1/7, plus 1/13, 1/17, and so on. So look at all of the primes. This is an infinite series. Well, since these partial sums are bigger than log n plus 1, and this term right here goes to infinity ever so slowly, but it does go to infinity as n goes to infinity, that says that we have a divergent series. And if it's a divergent series, in particular, there can't be finitely many terms in that sum. So that gives us another proof that there are infinitely many primes, but it tells us something more. It gives us some idea of the frequency of these primes. Because remember, if it's a very sparse set, then the infinite sum should converge, like a sigma 1 over n squared series converges. So you might notice that this growth rate, log of n, is exactly the same growth rate experienced by this infinite series. Sigma k equals 2 to infinity of 1 over k log k. So how do we see that? So remember back in calculus, if you wanted to estimate a sum of positive terms, you would compare it to the integral. So this is roughly equal to the integral from 2 to n of 1 over x log x dx. Okay, and well, what is the integral of 1 over x log x? You make a u substitution. U is log x, and so du is dx over x. And so this is just the integral of 1 over log u. And so this is just log of x going from 2 to n. And we can ignore this bottom term. And so the growth rate is log of n. So the sum of the reciprocals of the primes grows just like this series right here. And so you might expect that the kth prime perhaps is of order k times the natural log of k. And in fact, that's a true statement. So you can prove using the prime number theorem, and I'll state that a couple slides down the road, that the kth prime, p sub k, so I'll use that to denote the kth prime, is sandwiched between k times the natural log of k and k times the natural log of k plus k times the log of k. So that gives us a very good estimate for the size of the kth prime. And this result is highly non-trivial. I'm not going to try to prove that here, and we're not going to prove the prime number theorem either, but it is a proven statement. Okay, so let's return to the proof of the sum of the reciprocal primes. So we start with the following lemma. For any real number x between 0 and 1/2, I claim that minus the natural log of 1 minus x is less than x plus x squared. So recall the Taylor series expansion of the natural log. The log of 1 plus x is x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And that pattern continues off to infinity. So that's a standard result you would have done in Calc 2. And the series expansion is valid provided the absolute value of x is less than 1. So if we insert negative x for x, you would have minus x minus minus minus. All of the terms would be negative. And then if you insert an extra negative right here, that'll turn all of these into positive terms. So we'd have all positive terms right here. Factor out the x squared from all of the terms from this point onward. That'll leave me with 1/2, a 1/3 x, a 1/4 x squared, dot, 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 dot. And I claim that this sum right here is smaller than what? Well, you got a 1/2. Now x is less than 1/2, and so this next term is less than 1/4. This term would be less than 1/8, and so on. So this is all following because x is less than 1/2, and this sum right here adds up to 1, and so we get that this whole expression is strictly less than x plus x squared, establishing the lemma. Okay, we're going to use that lemma to prove the theorem. So now I next want to consider the following product. So where does this come from? The product, this is a product over all primes up to n of 1 minus 1 over p to the negative 1 power equals the product over the same set of primes of this geometric series, 1 plus 1 over p plus 1 over p squared plus dot, 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 dot. That is just the formula for the sum of a geometric series. And that sum formula is valid provided that r is less than 1. So notice 1 over p is always a value less than 1, and so this sum right here is a geometric series that adds up to 1 minus r to the negative 1 power. So that's all that's going on right here. Now I want to consider, what do you get for this product on the right-hand side? So let's just write out the first few terms. You got 1 plus a half 1 over 2 squared, dot, 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 dot. Okay, that's when p equals 2. That's the first prime. And then you're going to multiply that by what you get when you plug in p equals 3. And multiply that by the geometric sum with p equaling 5. And then multiply that by the geometric sum with p equaling 7, with p equaling 11, 13, and so on, all the way up to this sum prime, and I don't know what number that would be. Let's just call it pk for convenience. So this would be the biggest prime less than or equal to n. Okay, it's just a finite number of terms in this product. How do you multiply that out? So a typical term is obtained by taking one of the terms from the first sum times one of the terms from the second sum, etc. So I can get 1 by taking 1 times 1 times 1 times 1 times 1 all the way down the road. I can get a half by taking a half from the first term, a 1 here, a 1 here, a 1 here, all the way down the road. How would I get 1/3? I just take a 1 times a 1/3 times a 1 times a 1 times a 1 times a 1. How do I get 1/4? I take a 1/4 times 1 times 1 times 1 times 1. I can get a 1/5. I get 1/6 by going 1/2 times 1/3 times 1 times 1 times 1 times 1. And what you observe is that a typical term here, you'll have 2 to some power, you'll have a 3 to some power, you'll have a 5 to some power, and those powers can include the exponent 0. So some of the primes may not appear, but this would be your typical term. pk to some power here. Oh, I shouldn't use a k there. Let's call that L. And how far down do we go? Well, each of these is an infinite series. So you're going to have infinitely many terms in this sum. And will you get all of the natural numbers? or which natural numbers are you going to pick up when you multiply this out? Well, the only primes we have to work with here are the primes up to n. So I'm not going to get any natural number that has a prime larger than n. But what I can say is that I will certainly get all of the natural numbers up to n, because all of their prime factors are less than or equal to n. And you're never going to repeat one of those numbers more than once by uniqueness of factorization. So every one of these terms occurs exactly once in this product. And then we're going to have other terms, extra terms, and these would be natural numbers bigger than n. So natural numbers all of whose prime factors are less than or equal to n. And I really don't need to think much about those terms, because all I want to do is create a lower bound. And I can say that this is greater than or equal to the sum that we're starting with. All of these extra terms will be positive. Okay, so this finite product over the primes up to n is going to be greater than or equal to this sum right here. So let's keep that in mind as I go to the next slide. So this is what we just established. Okay, now 1 over k is greater than or equal to 1 over x for all x between k and k plus 1. So for x in this interval, k to k plus 1. All right, as x gets larger, 1 over x gets smaller than 1 over k. And so I can say that 1 over k is greater than or equal to the integral from k to k plus 1 of 1 over x dx. That's an interval of length 1 dominated by 1 over k. And so that's all that's going on this step right here, this inequality. Evaluate this integral. So I've collapsed a couple steps right here. And what is that? This is the natural log when you integrate 1 over x. So that would be log of k plus 1 minus log k. And you'll notice this is a telescoping sum. So the only terms that will be left after you do the cancellation are the terms at the endpoints. So when k is n, you get the natural log of n plus 1. And when k is 1, would be subtracting off the natural log of 1, which is 0. And so we simply get that this adds up to the natural log of n plus 1. So this product is strictly bigger than the natural log of n plus 1. Taking the natural log again of both sides, when you take the natural log of a product, we can bring down the negative 1 in the exponent. So I bring the negative 1 down, turn the log of a product into the sum of the logs, so sum of the log of 1 minus 1 over p. And on the right-hand side, we'd have the log of n plus 1. So when I write log, this is really a composite quantity here. And then we use our lemma. So our lemma says that minus the log of 1 minus x is less than x plus x squared. And so I insert 1 over p for the x. And remember, this is true provided x was less than 1/2. And 1 over p is always, or less than or equal to 1/2. 1 over p is always going to be less than or equal to 1/2 for any prime. Because the smallest prime is p equaling 2. So I use this inequality, insert 1 over p plus 1 over p squared. That's what this all would boil down to. And I get that sigma 1 over p plus 1 over p squared is greater than log of the log of n plus 1. And our goal was to estimate the sum of just the first term. So sigma 1 over p is bigger than log n plus 1 minus the sum over the second term. So sigma 1 over p over all the primes up to n is bigger than the log of n plus 1 minus the sum over the primes up to n. So p is a prime here, of 1 over p squared. So we're very close to completing the proof. We just have to observe that this sum here is a convergent sum, and you can easily estimate it to be less than 1 in size. So sigma 1 over p squared. In fact, if we sum over all primes, that would be bigger yet. What is this? This is 1 over 2 squared plus 1 over 3 squared plus 1 over 5 squared. Well, that's certainly less than or equal to the sum over all numbers Right, I'm throwing in more terms there, so this would be sigma k equaling 2 to infinity of 1 over k squared. And that's something we can estimate from calculus. That would certainly be comparing it to the integral from 1 to infinity of 1 over x squared dx. Just draw some little inscribed rectangles underneath the curve y equals 1 over x squared. 1, 2, 3, and so you just draw some rectangles like this. This would be 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. And how big is this integral? That's just minus 1 over x from 1 to infinity. So you'd get 0 as, technically you put a t here and let t go to infinity. You'd get 0 for that limit, and then subtracting the bottom limit, this is just equal to 1. So this infinite series here adds up to 1. And that completes the proof.